Welcome, ladies and gentlemen. This video is about geometric sequences and series, where the series is the sum of geometric sequences. We start with the geometric sequence, and this is defined by an, so the elements or the terms are defined by an is equal a times a factor q to the power of n. The n are integers greater or equal 0, and the a and the q, they are both not equal to 0, otherwise this is always the 0 sequence and it doesn't make sense. We write down a few terms of the sequence. So usually you write it here in short notation. Some people, they use these kind of brackets for the sequence. So we start with a times q power 0. Q power 0 is 1, so it's just a. Q power 1 is the q itself. And then you have q squared cubic to the power of 4, and so on. It never ends. It goes actually to n is equal infinity. So what does it mean? The geometric sequence is always just a multiplication by q of the previous term. So the next term is times q, the previous term. So in general, if you write it down, it means an plus 1. So the future term is the current one times q, or the next term, the previous one times q. And actually, if you divide this, next divided by current term is the q, and it is constant. So this means you always multiply by q. So this is all about the geometric sequence. Now we look to the sum. The sum of this, which actually is then called the series, as it goes to infinity. But first, let's look to the sum and then to the series. So, sum up all the terms. Up to index n. So what does it mean? In short notation, you sum from 0, because here it's q power 0, which is actually 1, up to n. So we have n plus 1 summands, n plus 1, because you start counting at 0. A times q power k. Some people, they don't like this a inside, and they pull it out, and you write the sum of the geometric sequence like that. It's also possible. Some start counting at 0 and write it extra and so on. There are different forms. Please be careful and check always how does it look like. So the main question here is there a closed formula? Is there a closed formula for this summation? Or do we really have to sum up all these terms? And the answer is yes, which can be easily derived, as you see in the following. So now we just consider actually without the a. We don't need the a. We check out if there is a closed formula for this summation only. And you start with k is equal 0, q power 0 is 1. Plus q. So everything without the a to save time. The last but one I want to write down, and the last term q power n. And let's say this is a sum up to index n. We just call it Sn. And what we're gonna do now is we multiply this line times q. And write it again. And now the trick is to subtract these two lines. And what remains here on the left side is 1. This is all canceling out, yeah? Blah, blah, blah. And what also remains is, besides the 1, is the q power n plus 1 term, but with a minus, because we subtract. First line minus second. On the right side, then we have Sn minus Sn times q, which actually simply can be written as Sn 1 minus q. And what do we have? The closed formula for this sum. This is what we wanted. So 1 minus q to the power of n plus 1 on the top divided by 1 minus q on the bottom. Let me see where to delete. Fine. Okay, so this is the closed formula for the summation of the geometric sequences. And now we go to the geometric series. So this means I want to study what is S infinity. If n goes to infinity, this is the geometric series. Okay, so how does it look like? It is 1 plus q squared plus q cubed and so on, and you never stop. So you can write it as the summation from k is equal 0 up to infinity now of the term q to the power of k. And this means it will be the limit of this closed formula, what we have computed before, yeah? So I need some space here. So it is the limit if n goes to infinity of this closed formula. 1 minus q n plus 1, 1 minus q. So the question is, what is the limit? In the denominator, it is just 1 minus q. So there is nothing to discuss. But in the numerator, you have to think. Why? Because it depends on the q. Yeah? So, for example, if the q is equal to, what is 2 to the power of n? 2 to the power of 2, 3, 4, and so on. It is always increasing, so this tends to infinity. But if the q, for example, is 1/2, then it's different, because the 2 to the power of n is in the denominator, and you might remember from limits of sequences that this tends to 0. So this means we need to generalize and give a condition for this q. When does this tend to 0 only? So I write it like this. This tends to 0 only if the q is less than 1. Because if it is 1, 1 to the power of n is still 1. And we are not really interested in the geometric sequence q is equal 1 because it's always constant. And it cannot be more, otherwise it is infinity. But it can also be negative, that's no problem. Then it's just changing the sign, but it must be greater, so bigger than -1. So we have proven that the sum of infinitely many terms is infinite. 1 divided by 1 minus q. And in order that you can imagine this also geometrically, so visually, we look at this series on a sheet of paper. So you imagine a square. So I'm gonna draw a square now. Let's say this square has lengths 1 and 1. We split the square in the middle. So what is the area above? Simply, you know it. It is 1/2. Now you split it again in here below. We split it here. What is the area here on the left side? 1 divided by 4. Split again. 1 divided by 8 here. Split this part again. 1 divided by 16. And again. So, and then I stop because I cannot write anymore. But you continue here splitting. Always into two similar or the same parts. So what do we have here? We have 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus, and you go on like that to infinity, and you know you cannot get out of this square, so the total sum is 1. And what is the connection now to the geometric series? Simply that. So this is 1/2 squared. The next one is 1/2 cubed. This is 1/2 to the power of 4. 1/2 to the power of 5 is 1/32, and so on. So the first one is to the power of 1. So if you look to the formula above, this is the same as a geometric series. So you can simply write this is 1/1 minus q. This is what we have proven. But be careful, if you look here, there was actually a 1 which was not included here because we started directly with index 1, not with index 0. So you have to subtract. You have to subtract here a 1. Yeah. That you can use the above formula. So just put the 1 to the right side here if you want. Perhaps here. Okay, but what is the q in our case? It is 1/2. You know it is converging by the result what we have considered before. So 1/1 minus 1/2 minus the 1. Simplify it. 1/1/2 is the 2, so 2 minus 1, yes. We have shown that this infinite sequence has limit 1, which is a converging geometric sequence. Thanks so much for your attention and see you in the next video.